Bismillahirrahmanirrahim. My name is Ishan Ahmad Arfi. I am pursuing PhD from University of Technology, Malaysia. My topic is rule-based enhanced energy management scheme for electric vehicles, fast charging workplace using battery stacks and solar power. The real-time power management scheme, it is a DC system for its many advantages considered in the recharging station due to overall efficiency of the system and encourages the integration of renewable power sources with fewer power converters. It sheds light by quick charging of electric vehicles integrated with energy storage stacks, photovoltaic system, and at the least priority given to the grid subject to the constraint scenarios. Contribution of the paper. It minimized the grid load during peak time. It subsidized electric vehicle recharging at a possible reduced cost. It raised the profitability of the recharging station, reallocates energy to the vehicle charger through online monitoring, ensure optimal control of existing power, reducing charging time and grid sustainability. To charge a power plug-in electric vehicles using less power from the grid using a demand side strategy to enhance grid stability and its priority level assigned to the vehicle for optimal charging. Overview of the paper, it shed light by the quick charging of electric vehicles integrated with energy storage stacks, photovoltaic system, and at the least priority given to the grid subject to the constant scenarios. PV modules, it harvests DC power via maximum power point tracking controller, extracting PV power to facilitate the recharging of electric vehicles from a substation. This is the four models taken for this in this scheme, and the and the initial state of charge is depicted in the figure. This is the 24 hours 1 day scenario of how much PV power harvesting from the from the solar. This is the diagram, one line diagram, the overall diagram of the rule-based real-time rule-based power management scheme. It's a PV panels harvest the DC-DC converter. It extracts the PV power from perturb and observe controller. And similarly here, this is a two-way from the energy state, the power charging and power discharging via power DC-DC converter. And the inverter this is a invert converter, act as an inverter when it connect to the grid, and the DC to DC converter connected to the electric vehicles. A vehicle, and this is bidirectional. It gives power to the grid, and it is vehicle to grid, and then it takes the power from the grid and DC grid to vehicle. The controller, the rule-based energy management controller, is embedded in this controller. The yearly solar irradiance and ambient temperature of studied area. This is the whole the complete total hours in the year. Complete total hours. The solar irradiance. This is the profile of solar irradiance of the studied area, and this is the ambient temperature of the studied area taken in degree centigrade. The single diode model, the equivalent diagram, the diode model tandem solar cell. The sun is extracting the energy from the sun. This is a diode. The two series resistance and the shunt resistance, and from the IPV and DPV we get the power by multiplication of voltage from the PV and the current from the PV, and we get the power. This is the equations of IPV, I photon, I saturation current, these are time temperature, it's the Boltzmann constant. These are the taken, and it's a diode quality factor. These are the equations we take from the single diode model, equivalent single diode model. It's a control strategy of energy storage units. The PI controller proportion integral gain, how it when it charge, when it discharge, the lower upper limit and lower threshold, and the DC is converted, and it check the upper limit and lower limit accordingly. It charges and discharges the power. This is arrival and departure rate of electric vehicles. The probability density function of the arrival rate of the electric vehicles and the departure rate of the electric vehicles, time taken in hours. This is the PDF tag. This is an arrival scenario, and this is a departure scenario taken in time. Vehicle, the number of electric is 150, time in hours, a single day. This is number of electric vehicles. 150. In this case, we take 150 electric vehicles. The grid demand when the grid is saturation state. When the grid is unsaturated state means off peak time, off peak or on peak, at concentrated at congestion state or at uncongestion state, the 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 grid demand is depicted in this figure. Rule-based power management scheme. It is a deterministic rule-based, simply called rule-based algorithm dictates exactly what will happen under different scenarios. The energy management problems are tackled by dispatching sources mainly based on the set of rules where real-time decisions are directly made without implying optimization practices. The rule-based is problem specific and needs to redefine for different problems. However, there is no requirement of data prediction for the implementation of rule-based algorithm, thus it is suitable for decision making in a real-time environment. Merits of rule-based power management scheme. It lessens the grid stress during peak load intervals. It facilitates electric vehicle owner to charge their vehicles at a considerable less price. It raises the income of the refueling station, assigns power to the car battery via online supervising to ensure optimal utilization of existing power, charge interval, and grid reliability. It charges the plug-in electric vehicle using less power from the grid and usage of more renewable energy resources with a demand-side strategy to enhance energy efficiency and also stability. This is, these are 6 core operating scenarios here. The one is called over demand. Over demand number scenario. Number 2 is the shared demand scenario. Number 3 is the no demand scenario. Number 4 is the dead demand scenario. Number 5 is the grid demand scenario, and 6 is the limited power demand. That is power injected to grid when this condition fulfills, when the grid power threshold is less than equal to grid power. It means that it can take power. Description of core scenarios. In over demand scenarios, it accelerates, it active when electric vehicle demand is far greater than PV power. Shared demand activates when electric vehicle demand exists but is smaller than or equivalent to PV power. No demand scenario exists when the PV power is in abundance but the electric vehicle demand is zero. Means that it is a holiday. It is a holiday when there is no electric vehicle in the charging in the station. That demand it executes when both electric vehicle demand and electric PV power is zero. Means that it is considered as a holiday day and in the night time. Grid demand mode, the energy management controller remove the stationary battery stacks to escape from damage when the state of charge of the battery unit decreases below 10%. In such cases, the public grid be utilized as a complementary source to balance the power acquired by a load of the maximum priority. Partial power mode, when the supplied power to the main streams is greater than the authority by the grid operator, the energy management controller disconnects the MPPT regulator and minimizes the energy generator by the PV module, so activating the limited power substate. This is the flow chart of major modes of real-time power management algorithm. First of all, we load electric vehicle demand loaded file and the PV power of the whole year, and similarly holidays of the whole year, number of working days of the whole year, and the electric and the grid demand or grid load of the whole year. We load all this load. Then the 6 major modes are taken, in which, for example, this mode is the over demand mode. Is in this mode the solar power to electric vehicles is activated, the battery storage to electric vehicles is activated, and grid to electric vehicles also activated. In the last mode, for example, power injected to grid, the grid is off peak, and the grid to energy storage stack and grid to electric vehicle and battery storage to electric vehicle is activated in this. After that, when 6 modes are activated by concurrently or simultaneously or one by one, then we calculate the profit by calculating the purchasing price purchasing price and selling price, and profit by divide minus selling price minus purchasing price divided by 100 to convert the cents into the dollar, and then the profit is calculated. This profit is calculated, and this is the overall case. This is the example of how the PV power energy goes to the electric vehicles. Similarly, the energy storage unit to electric vehicles and grid to electric vehicles. In this case, this is because the case is for 1 week, and the case for 1 week, and it is a sunny weather. The sunny weather, the sun is the sun is at high peak, so there is no need to take the power from the energy storage unit. And this is the overall diagram. Is the flow chart of the major modes taken of when the difference of power is greater than 0, and when the storage, what happened when the storage stack is saturated, what happened when the storage stack is unsaturated. So what are happening, how the modes are working in this scenarios, these are depicted in the flow chart of the statistical scheme. And that's all. Thank you very much, and thank you very much. Terima kasih.